One of the most common misconceptions about quantum mechanics is that an observation is simply one particle interacting with another particle. This false impression misses the true essence of what makes quantum mechanics philosophically intriguing. Suppose we have a quantum randomizer which causes our particle to go in one of two directions. Now let's add a second particle to our system. The first particle will interact with the second particle. The moment these two particles interact, we say that they are entangled with one another. This is because if the first particle had gone in the other direction, then the trajectory of the second particle would be completely different. By just observing the second particle alone, this will be enough to know which of the two directions the first particle went in. The second particle therefore acts as a detector for the first particle. But what if we choose not to observe either particle? According to quantum mechanics, each particle will simultaneously be in a combination of both possibilities, which we call superposition. Now, suppose we observe one of the two particles. The superposition disappears, and we always see only one of the possibilities. The two particles interacting with each other is not what counts as the observation. After the two particles interact, both possibilities still exist, and it is only after the observation that only one of the two options becomes certain. After the two particles interact, we only need to observe one of the two particles to know about the state of both of the particles. We refer to this by saying that after the two particles interact, they are entangled with one another. This is similar to the spins of two particles being entangled with one another. The spin of a particle in a particular direction can be observed to have only one of two possible values. These values are spin up and spin down. Suppose we also have a second particle. There are now 4 different sets of possible observations. Just as our previous example could simultaneously be in a superposition of 2 different states when we were not observing it, this system can simultaneously be in a superposition of 4 different states when we are not observing it. Suppose we briefly observe only the particle on the right. Suppose we see that the particle on the right is spin up. This means that 2 of the 4 possibilities disappear. The quantum system is now simultaneously in a superposition of only two possibilities. The quantum system shown here does not contain any entanglement, because measuring the spin of one of these two particles will not tell us anything about the spin of the other particle. Let us use one of these particles as a detector to determine the spin of the other particle. As we bring the particles together, if the two particles are spinning in the same direction, then our experimental setup will cause the particle on the right to change its spin to the opposite direction. But if the two particles start out spinning in opposite directions, then nothing will change. When we start out, the particle on the right is known to be pointed up, whereas the spin of the particle on the left is unknown. The system consists of both of these possibilities existing simultaneously. If we run our experiment without observing either particle, the system will continue to be in a superposition of two possibilities existing simultaneously. But regardless of which of the two states the system started in, after these particles have interacted with each other, they are guaranteed to be spinning in opposite directions. We therefore now only need to observe one of the two particles to know the spins of both particles. As a result, after the two particles have interacted, we say that they are entangled with each other. Suppose we allow these two particles to interact and become entangled, but we do not observe either particle. The system consists of both of these possibilities existing simultaneously. It's only when we observe at least one of these particles that the outcome of the entire system becomes certain. According to the mathematics of quantum mechanics, this remains true regardless of how many particles we have. A detector simply consists of a large number of particles. This means that if we have two entangled particles, measuring the spin of one of the particles with a detector will not necessarily tell us the spins of the two particles. If we are not observing the detector or the particles, then the two particles will simply become entangled with all the particles inside the detector in the same way that the two particles are entangled with each other. According to the mathematics of quantum mechanics, both sets of possible outcomes will exist simultaneously. Suppose we observe the detector, which means that we observe at least one of the many particles that the detector is made of. Once we observe the detector, all the particles inside the detector and the two spinning particles that we originally wanted to measure will all simultaneously collapse into one of the two possibilities. According to the mathematics of quantum mechanics, it does not matter how many particles the system is made of. We can connect the output signals of our detectors to large complex objects, causing these large objects to behave differently depending on the measurements in the detector. According to the mathematics of quantum mechanics, if we do not observe the system, both possibilities will exist simultaneously. At least until we observe one of the many entangled particles that make up the system. Here, once the particles become entangled, the two different possible quantum states are represented by the colors yellow and green. The yellow particles pass right through the green particles without any interaction. The yellow particles pass right through the green particles without any interaction. After the entanglement occurs, the system is represented by a wave function in a superposition of two different quantum states, represented here by yellow and green. One wave is not really above the other, but this visualization illustrates how the yellow quantum state is unable to interact with green quantum state. Since the yellow wave can't interact with the green wave, no interference pattern is created with the detectors present. On the other hand, with the detectors removed, the entanglement with the detectors never happens, and the system does not split into the yellow and green as before. The resulting waves are therefore able to interact and interfere with each other. Two waves interacting with each other creates a striped pattern. This is why a striped probability pattern is created when particles pass through two holes without any detectors present. And it's why a striped probability pattern is not created when particles pass through two holes with detectors present. Having just one detector present has the same effect as having two detectors. This is because it only requires interaction with a single particle in order for entanglement to occur. But even after a particle interacts with a detector consisting of many different particles, the system is still in both states simultaneously until we observe one of the detectors. There's considerable debate as to what is really happening, and there are many different philosophical interpretations of the mathematics. In order to fully appreciate the essence of this philosophical debate, it's helpful to have some understanding of the mathematics of why entanglement prevents the wave functions from interacting with each other. The probability of a particle being observed in a particular location is given by the square of the amplitude of the wave function at that location. In this situation, the wave function at each location is the sum of the wave functions from each of the two holes. Although there are many different places that the particle can be observed, to simplify the analysis, let's consider a scenario where the particle can be in only one of two places. This scenario is similar to the scenario measuring the spin of a single particle, in that there are only two possible outcomes that can be observed. The state of spin up can be represented by a 1 followed by a 0. The state of spin down can be represented by a 0 followed by a 1. Similarly, we can use the same mathematical representation for measuring the location of our particle. We will signify observing the particle in the top location with a 1 followed by a 0. And we will signify observing the particle in the bottom location with a 0 followed by a 1. Let's now add a detector indicating which of the two holes the particle passed through. We're going to observe both the final location of the particle and the status of the detector. There are now a total of 4 different possible sets of observations. This is similar to how we had 4 different possible sets of observations when we had 2 spinning particles. Although our detector is illustrated as a large object, let us suppose that this detector consists of just a single particle. In the case of the 2 spinning particles, each of the 4 possible observations can be represented with a series of numbers, as shown. The same mathematical representation can be used in the case of observing the position of our particle and the status of our detector. Here, we need 4 numbers because there are 4 possible outcomes when the status of the detector is included. But if we didn't have the detector, we would only need 2 numbers because there are only 2 possible outcomes. This is the same way in which we need 2 numbers for a single spinning particle. If the single spinning particle is in a superposition of both states simultaneously, then this is represented mathematically as shown. The c variables are constants. The probability of observing the spin of the particle in each of the 2 states is given by the squares of the magnitudes of these constants. If we have 2 spinning particles, we can have 4 possible observations, each of which is represented with a sequence of 4 numbers as shown. If the system is in a superposition of all 4 states simultaneously, then this is represented with the following mathematical expression. As before, the c variables are constants. As before, the probability of observing the spins of the particles in each of the 4 states is given by the squares of the magnitudes of each of these constants. This same mathematical representation can be used to describe observing the location of the particle and the state of the detector. Here, the c variables represent the values of each of these wave functions at the final location of the particle. When the system is in a superposition of these 4 possibilities, it is represented mathematically as shown. But if we never had the detector, then each quantum state would be represented by only 2 numbers instead of 4, since there are only 2 possible observations. As before, the c variables represent the values of the wave function from each of the 2 holes at the final locations of the particle. Without the detector, if the system is in a superposition of both quantum states simultaneously, it's represented mathematically as follows. Here, if one of the c variables is positive and another c variable is negative, they can cancel each other out. On the other hand, the C variables would never be able to cancel each other out with a detector present. With a detector present, even if one of the C variables is positive and the other C variable is negative, their magnitudes always strengthen each other when calculating the probability of observing the particle at a certain position. But without a detector, if one of the C variables is positive and the other C variable is negative and their magnitudes are equal, then they will cancel each other out completely and provide a probability of 0. If the particle is not limited to being at just 2 possible positions, then there will be certain locations where the C variables representing the values of the 2 wave functions will cancel each other completely. This is what allows a striped probability pattern to form when there is no detector present. And it's also why a striped probability pattern does not form if there is a detector present. Note that nowhere in this mathematical analysis was there ever any mention of a conscious observer. This means that whether or not the striped pattern appears has nothing to do with whether or not a conscious observer is watching. The presence or absence of a detector consisting of just a single particle is enough to determine whether or not there is a striped pattern. A conscious observer choosing whether or not to watch the experiment will not change this outcome. But because the mathematics says nothing about the influence of a conscious observer, the mathematics also says nothing about when the system changes from being in superposition of multiple possible outcomes simultaneously to being in just one of the possibilities. When we observe the system, we always see only one of the possible outcomes. But if conscious observers don't play any role, then it's not clear what exactly counts as an observation, since particles interacting with each other does not qualify. There's considerable philosophical debate on the question of what counts as an observation, and on the question of when, how, and if the system collapses to just a single possible outcome. Much more information on this topic is available in the other videos on this channel, and please subscribe for notifications when new videos are ready.